On October 21st, 2025, Earth entered total blindness. 6 weeks of silence where every telescope from Hubble to James Webb lost sight of the sun. And in that glare, 3I Atlas, a 33 billion-ton interstellar object, vanished. Its chemistry defies every known comet. Its path through the solar system is too perfect. Scientists called it coincidence. Others called it a maneuver, because while the world went dark, 3I Atlas may have used that moment to do the unthinkable, change its path. As October faded into silence, Earth's greatest observatories went dark. The countdown had already begun. For the next 6 weeks, every eye humanity has turned toward the cosmos, from Hubble and James Webb to the Vera Rubin Observatory, would be blinded by the sun itself. And right in that window, 3I Atlas reached the most critical phase of its journey. It wasn't a malfunction, nor a technical failure. This blackout was written in geometry. When 3I Atlas crossed behind the sun, its position from Earth's perspective dropped to less than 1 degree of separation, so close that even radar, infrared, and high-energy sensors drowned in a sea of light. The sun's corona, hotter than 1,000,000 degrees, erased every trace of signal. For the next 40 days, 3I Atlas might as well not exist. To most scientists, this was just bad luck, a frustrating coincidence of orbital timing. But to others, it was something else. If any object wanted to alter its path unseen, this was the perfect moment to do it. Hidden behind the solar glare, 3I Atlas could perform a maneuver, a controlled burn, a course correction, and no one would know until it emerged again. And the strange part, the data leading up to the blackout had already begun to change. In mid-September, the James Webb Space Telescope captured its infrared spectrum, and what it found didn't fit the rulebook. The ratio of carbon dioxide to water was 8:1. No comet in recorded history has ever shown chemistry like that. Water usually dominates. Here, it was barely present. Instead, the signature of CO2 burned bright, along with traces of carbon monoxide and carbonyl sulfide, chemicals rarely seen together at this scale. NASA's internal chat logs reveal hesitation. The data almost got buried to avoid panic, but it was too important to ignore. Then Japan's KK Observatory detected something even stranger: bright emission lines of nickel with almost no iron at all. For every natural comet, iron and nickel exist together in consistent ratios. But here, the balance was shattered. Pure nickel dominating the readings. That anomaly broke every model of cosmic chemistry. And still, that wasn't the end. High-resolution imaging from Hubble showed a smooth, teardrop-shaped coma. A perfect, symmetrical glow instead of the ragged, jet-filled chaos typical of natural comets. No violent ejections, no spinning debris. Just a calm, steady envelope of light, as if something were controlling its release. By early October, Mars orbiters caught the last clear views before the blackout. The coma's outgassing remained steady, directed sunward, narrow, and focused. Almost aimed. And then, on October 21st, the sun swallowed everything. The screens went blank, the data stopped, and humanity was left staring into the light, waiting for the darkness to end. If 3I Atlas truly intended to change its path, it would do so right now, in perfect secrecy. By the time October 29th, 2025 arrived, the world's eyes were blind. The sun stood directly between Earth and 3I Atlas, a cosmic curtain drawn across the most important event in modern astronomy. Inside that glare, beyond the reach of every sensor and telescope, the third known interstellar object moved toward its perihelion, its closest pass to the sun. And that's where everything could change. The blackout wasn't symbolic. It was total. Even radar systems, the last resort for tracking near-solar objects, failed to detect a single echo. The solar corona, a chaotic plasma field nearly 1,000,000 degrees hot, scattered radio waves like smoke in the wind. Infrared sensors aboard James Webb couldn't penetrate the radiance. Even the Parker Solar Probe, orbiting closer to the Sun than any human-made craft in history, couldn't risk turning its instruments toward the light. For 6 weeks, Earth was deaf and blind. But before that silence, scientists had already seen enough to know something was wrong. Each dataset from JWST, KK Observatory, Vera Rubin, and ESA's Mars orbiters told the same story. A comet that behaved like no comet ever recorded. Its outgassing pattern wasn't random, it was directed. Its chemical makeup, dominated by carbon dioxide and nickel, defied natural models. Its trajectory, nearly aligned with the solar plane, looked deliberate, and its rotation, slow and uniform, suggested a body not tumbling freely through space, but maintaining stability. By late October, theories began to split. NASA's internal bulletins described 3I Atlas as an unprecedented thermochemical outlier. The Galileo project, however, used a different word: candidate. In private calls leaked weeks later, researchers debated whether this could be a controlled object, capable of exploiting the sun's gravity to change its velocity. The math supported it. At 68 kilometers per second, 3I Atlas would experience the Oberth effect, the same principle that allows a spacecraft to gain or lose massive amounts of energy by firing its engines near a gravity well. If any propulsion occurred at perihelion, even briefly, the resulting slowdown could trap the object inside the solar system. It would no longer be a visitor, it would be a resident. But that idea remained only theory until the blackout began. From October 21st onward, data vanished. No optical readings, no radio echoes, just silence. And in that void, speculation filled the gap. Across social media, images of green auroras and faint comets multiplied. Some claimed to see fragments trailing 3I Atlas. Others spoke of solar flares timed too perfectly. Astronomers dismissed the noise, but even among professionals, unease grew. The alignment of events was too neat: peak solar activity, 3 coronal mass ejections, and a total loss of visibility just as the object reached its most critical point. Inside NASA, a small working group continued to model possibilities in the dark. They simulated every known scenario: natural fragmentation, outgassing pressure, even impacts with solar debris, and still couldn't reproduce the expected trajectory if the object decelerated. The only variable left was intent. But intent requires control, and control implies technology. The silence stretched on. The last timestamp from the Mars Trace Gas Orbiter read October 20th, 2357 UTC. After that, nothing. For the next 40 days, Earth could only wait, staring at the blinding face of the sun, knowing that somewhere within that light, 3I Atlas was moving. Whether it was drifting, breaking apart, or burning its engines, no one could tell. When it reemerges in December, even the slightest deviation, a flicker of light, a change in speed, a shift in direction, could rewrite everything we thought we knew about what passed through our solar system. And until then, the only thing louder than the sun's roar is the silence that follows it. When December arrives, the waiting will end. For 6 long weeks, Earth will see nothing: no light, no signal, no trace of the third known interstellar visitor behind the sun. But when 3I Atlas finally reemerges from that blinding veil of solar fire, the truth will begin to unfold. Every major observatory is already preparing for that moment. NASA's Deep Space Network has cleared schedules, reserving antennas across California, Madrid, and Canberra. The Vera Rubin Observatory has dedicated its first survey of December to the coordinates where 3I Atlas should appear. And the Galileo project, led by Loeb, plans to cross-check every new data point the instant light returns, because what happens next will decide everything. If the trajectory matches predictions, the story ends in ordinary physics. A hyperbolic visitor deflected by the sun and now racing into deep space forever. But if the coordinates are even slightly off, if its speed has dropped or its path has curved, then something happened in the dark. Something no telescope saw. Something not natural. The smallest deviation, just a few kilometers per second, would change everything. It would mean that while Earth was blind, 3I Atlas altered its energy. And in the language of celestial mechanics, that's impossible without force. A comet can't slow itself down. Outgassing jets can nudge an orbit by meters per second, not thousands. So if that slowdown exists, it implies intent or technology. Every mission team knows the stakes. They're preparing baseline comparisons of pre-blackout data, nickel lines, carbon dioxide ratios, coma symmetry, and brightness curves. Even a small chemical shift could indicate transformation, fragmentation, collapse, or controlled release. But there's another layer to the anticipation: fear. Because if 3I Atlas truly used the Oberth effect to burn near the sun and change its velocity, it may no longer be leaving. It may be staying, bound to the inner solar system, unseen, until the next alignment exposes its new orbit. For now, all anyone can do is wait. Wait for the sunlight to fade. Wait for the glare to lift. Wait for the sky to tell us whether the impossible has just happened. In total silence. As the final days of October fade away, the world waits. Every observatory, every astrophysicist, every telescope operator on the planet has their eyes on December, the moment when 3I Atlas will emerge from behind the sun. Until then, it's all models, equations, and silence. For weeks, supercomputers across NASA, ESA, and the Galileo project have been running non-stop, simulating what could have happened during the blackout. Each simulation begins the same way. A 33 billion-ton interstellar object approaches the sun at 68 kilometers per second, fast enough to leave the solar system forever. But then comes the question no model can ignore. What if it didn't leave? In theory, a comet like 3I Atlas should have been flung outward by the sun's gravity, accelerated by heat and radiation pressure. But if it slowed down instead, even by a few percent, the result would be catastrophic for the equations that define celestial mechanics. It would mean something interfered, something powerful enough to rewrite its trajectory. NASA's Solar System Dynamics Lab has been reviewing pre-blackout data frame by frame. Tiny anomalies appear in the last hours before the signal vanished. Subtle fluctuations in brightness, changes in coma structure, and a brief drop in tail symmetry that doesn't match normal outgassing patterns. Each hint points toward a singular possibility. An event occurred at perihelion, hidden behind the solar glare. Whether natural or engineered, it changed 3I Atlas. The Galileo project has taken it further. Using AI-assisted modeling, their team has calculated the exact energy drop required to convert 3I Atlas from a hyperbolic escape trajectory into a bound orbit. The number is staggering, a velocity reduction of roughly 20 kilometers per second. For a natural object, that's impossible. For a controlled one, it's efficient. Dr. Loeb calls it the solar Oberth scenario. In his notes, he describes a hypothetical vehicle that could use the sun's immense gravity to perform a braking maneuver. By firing engines or releasing directional energy at perihelion, it could shed enough velocity to stay captured within the inner solar system. It wouldn't need to fight gravity. It would use it. And that's what terrifies everyone watching. Because if that maneuver actually happened, it means 3I Atlas is no longer a visitor. It's a permanent resident. Officially, NASA's public updates remain calm. They describe the blackout as a routine observational limitation, a temporary loss of visibility expected to end in early December. But internal documents tell a different story. In an October 17th memo leaked from the Planetary Defense Coordination Office, analysts discuss preliminary contingency scenarios for the object's possible capture. One section references long-term orbital integration simulations extending centuries into the future, a sign that, at least behind closed doors, they're preparing for the possibility that 3I Atlas isn't leaving at all. Meanwhile, public speculation grows. Astronomy forums have become battlegrounds of belief and denial. Some users point to the perfect alignment of events, blackout, solar flares, spectral anomalies, as proof of an artificial mission. Others argue it's all coincidence amplified by social media. But even skeptics admit the chemistry doesn't fit. The last confirmed measurements before the blackout showed nickel dominating iron, an inversion unseen in natural comets. And the carbon dioxide to water ratio of 8:1 remains a physical impossibility under standard solar heating. Those aren't signatures of a frozen rock, they're fingerprints of manufacture. Now, as the countdown continues, observatories across the world are synchronizing for December 5th, the predicted date when 3I Atlas will re-emerge from the sun's glare. They'll be watching for one thing: deviation. If its position matches the old models, the story ends with data. But if it's even a fraction off, if its motion suggests it slowed, turned, or fragmented, the story begins again, under a far stranger light. The silence of space will finally break. The sun will dim enough for light to return. And somewhere in that re-emerging glow, 3I Atlas will reveal what it truly became. Because if it used the sun to stop, then this isn't just another interstellar traveler. It's the first to arrive and stay. By late November 2025, the world has grown used to waiting. The sun still blinds every telescope pointed its way, and 3I Atlas remains hidden behind its blazing curtain. 6 weeks of silence, 6 weeks of guessing, modeling, and hoping that when the light finally returns, the universe will still make sense. Inside control rooms across NASA, ESA, and the Galileo project, tension has hardened into routine. Every day begins the same. Recalibrate sensors, test communications, update simulations, and check the solar elongation angles to see if the window has begun to open. Not yet. Each morning brings the same verdict, still too bright. But even without a single new image, the data keeps evolving. Tiny perturbations in the sun's magnetic field, recorded by the Parker Solar Probe, hint at a disturbance deeper than expected. A localized interaction near the plane of 3I Atlas's trajectory. It's not confirmation, but it's enough to make scientists uneasy. Dr. Avi Loeb puts it bluntly in a recent interview. If the object performed any maneuver at perihelion, we wouldn't know until December. But by then, it will already have rewritten the map. Those words spread fast, feeding both excitement and fear. Media outlets label 3I Atlas the invisible enigma. Every forum is filled with predictions, some scientific, some apocalyptic. One theory dominates them all, that during the blackout, it changed course. Within NASA, internal bulletins grow increasingly cautious. The official tone has shifted from routine observation gap to active monitoring of reemergence phase. Teams are now preparing contingency reports for 3 possible outcomes. 1. No deviation. 3I Atlas exits exactly as predicted, confirming a natural trajectory. 2. Partial deviation, a measurable slowdown or directional drift that defies cometary dynamics. 3. Full deviation, a captured orbit, meaning the object used the sun to stop. It's that third scenario that keeps researchers awake at night. If confirmed, it would mean an interstellar body now moves among the planets, not by chance, but by design. Meanwhile, in Chile, the Vera Rubin Observatory prepares for its most anticipated scan yet. On December 3rd, it will turn toward the dawn sky for the first post-blackout capture. Engineers are testing exposure sequences, calibrating filters, and syncing observation windows with the Deep Space Network. Everything must be perfect. Every second of data will matter. And as humanity waits, nature adds to the unease. Solar activity continues to surge. 3 new coronal mass ejections have erupted in November alone, scattering streams of charged particles across the inner solar system. To some, it's just coincidence, the sun's usual chaos. To others, it feels almost synchronized. By the end of the month, the line between science and speculation blurs. We know what should happen, but we've known that before and been wrong. If 3I Atlas reappears where it should, the universe remains predictable. If it doesn't, then something changed when no one was looking, and so we wait for the light to return, for the first image to break the silence, and for the answer to the question that has haunted every sleepless night since October. Did 3I Atlas simply pass through our solar system, or did it decide to stay?